In this video, we're going to discuss what happens with the vapor pressure when you have a mixture of two volatile materials. So two liquids that normally would have their own vapor pressure. So you can imagine you have one container, water or something like that, and it has a little bit in the gas phase. And you could have a second container, ethanol or methanol, and it's going to have some amount in the gas phase as well. So we'll arbitrarily say we're just at room temp. Well, different materials will have different vapor pressures at the same temperature. It's dependent on where their boiling point is, what their delta H of vaporization is. Let's imagine that at this temperature, one of these had a vapor pressure equal to 100 torr. The other, however, has a vapor pressure equal to 400 torr. If I had a bottle of pure purple over here, I'd have 400 torr of vapor pressure. If I had a bottle of pure white, I'd have a vapor pressure of 100 torr. Well, let's mix them. So I set it up, I make a mixture, and we're going to say it's 2/3 the white material and 1/3 the purple. This means we could find mole fractions. And so we'll just say that I have 4 moles of the white material, I have 2 mole of the purple material. So my total moles is 6 moles of stuff. That means I can find the mole fraction. It's going to be 4/6, or 0.67. And I can find the other mole fraction. That's going to be 2/6, or 0.33. Well, each individual gas will obey the law. We'll say that, hey, the actual vapor pressure for the white material is going to be equal to its pure vapor pressure times its mole fraction. And that's going to be true. The actual vapor pressure, purple material, is going to be equal to its pure pressure times its mole fraction. Let's give these some terms. Let's call it A and let's call it B. So this will be material B, this will be material A. Well, if I mix it, there's still some amount of each in the gas phase. The fact that there's another thing in the gas phase is irrelevant. The vapor pressure achieved by your material is going to be the same at a given temp, regardless of there being an atmosphere above it or not. Which means compound A is not affected by compound B in terms of what its vapor pressure will be, other than the mole fraction change. We don't care that there will be some B floating around in the headspace. This means that there's a pressure total, and that's just going to be the actual pressure A plus the actual pressure B. Had it been 100% A, I would have added nothing, and my total pressure would have been 100. Had it been 100% B, I would have added nothing from A, and it would have been 400. As each of these is modulated, I'm going to have some amount of gas from each material, and they're just going to sum together for the total. What's that actually going to play out here as? Well, let's calculate. For A, that normally would be 100 torr, but it's only got 2/3 of its mole fraction, so it's blocked. Some of the attempts for compound A to escape aren't compound A, and so they don't have compound A escape. And so in reality, we only get 67% of them to escape, which means the real pressure becomes 67 torr. For compound B, well, it normally was 400 torr, and it's only 0.33%. So it's going to get 1/3 of that, or about 132 torr. So because compound B was 1/3 of the mixture, it got 1/3 of its vapor pressure. Because compound A was 2/3 of the mixture, it got 2/3 of its vapor pressure. And the total vapor pressure The total pressure exerted by all the gases in the headspace is going to be the sum of the two, about 200 torr. When you have a mixture of volatile materials, your total vapor pressure is going to be somewhere in between the two pure vapor pressures. As long as we can figure out what the mole fraction of each is and what its original pure vapor pressure would be, we can always find what its actual vapor pressure is and then just sum those two to get the total. And so the only really complicating factor when we have, say, two liquids mixed with each other is that the total vapor pressure is the sum of the individual vapor pressures. When we have a liquid with a non-volatile material like salt or sugar, well, the vapor pressure is just equal to the one volatile material's vapor pressure. So watch your terms, whether you're referring to the vapor pressure of one of the compounds or whether you're referring to the vapor pressure total for the mixture. Two liquids mixed together will have a total vapor pressure that is the sum of the individual vapor pressures of the two.